Counterfeiting poses significant risks to public safety and health, with counterfeit goods penetrating untrusted supply chains through intricate logistical distribution channels. Researchers have proposed various anti-counterfeiting solutions, including special inks, laser engravings, and optically variable features. However, these methods add overhead to the verification pipeline and often require specialized techniques, restricting supply chain stakeholders' participation. In contrast, paper-based authentication systems leverage microscopic imperfections in paper surfaces to authenticate products, offering an economical solution. This work aims to systematically unify two separate research areas, creating unclonable identifiers and securing virtual records using distributed ledgers. The authors introduce a generalized paper-based authentication framework, identifying important shortcomings and promising ideas in existing literature. They conduct a stage-wise security analysis, drawing inspiration from signal processing, cryptography, and biometric systems. The supply chain is demarcated into two distinct worlds: the physical world, where the product resides, and the cyber world, which houses records detailing product movements. A holistic understanding of the security of both worlds is essential, as they interact regularly. The authors examine the physical world, discussing extrinsic identifiers such as barcodes, QR codes, and RFID tags, which have severe security shortcomings due to their unencrypted design. They also explore intrinsic identifiers, including special materials with unique visible features, such as bubble tag and fiber tag. The authors highlight the limitations of extrinsic identifiers, motivating a solution that adds minimal overhead to the supply chain, is easy to acquire, and provides adequate authentication performance. They propose using physically-unclonable identifiers, PUFs, of paper surfaces, which offer a secure and robust solution. The paper-based authentication framework is designed to evaluate and categorize existing anti-counterfeiting systems, creating an extensive taxonomy and outlining crucial security vulnerabilities overlooked in the existing literature. The author's main contributions include systematizing knowledge, classifying and analyzing anti-counterfeiting methods, and exploring practical systems representing real-life supply chain scenarios. They also examine key representative scenarios, illustrating the range of practical and technical challenges in real-world supply chains, and outline best practices to guide future research. Here is a combined summary of the 2 pages. Intrinsic identifiers, specifically optical physically unclonable functions, PUFs, are a class of candidates that satisfy the properties of being unclonable and unique. PUFs have been widely used as primitives for cryptographic protocols, such as key distribution. In a challenge-response scenario, these functions model light as a challenge signal applied to physical material to obtain output responses that are difficult to replicate due to uncontrollable intrinsic material properties. Existing work has largely focused on paper surfaces due to the ease of modeling its interaction with light. The extraction of the inherent randomness of the paper surface has been studied using both physical modeling and visual appearance. Physical intrinsic features model the surface texture of the physical material directly. One of the first works to extract the microscopic level texture of a paper surface as a unique signature is by Clarkson et al., who use commodity scanners to acquire 4 views of the image at 4 different orientations. The limitations of extrinsic PUFs motivate the consideration of intrinsic PUFs as a scalable alternative. Paper-based anti-counterfeiting solutions are inspired by the economical nature, simplicity of physically modeling interactions with light, and abundance of prior studies. However, the assumption that micro-level intrinsic features extracted from the paper surface are unclonable has not been explicitly justified. The papermaking process is an elaborate process that combines different intricate chemical and mechanical steps. The process can be abstracted into 6 steps, with the largest amount of randomness introduced during the process of forming. Uncontrollable differences arise between different paper sheets at every stage of the pipeline, with the forming process introducing the most randomness. To understand the suitability of paper microstructures as an optical PUF, standard PUF metrics such as robustness and uniqueness are evaluated. The robustness metric measures the stability of the output under different evaluation conditions, while the uniqueness metric measures the discriminative power of the PUF. The evaluation metrics inform a system designer about the feature variations, which shine a light on the feasibility of using a feature for authentication. The use of intrinsic paper PUF identifiers is justified by examining the papermaking process and identifying the key step that introduces randomness into the microscopic texture of a paper surface. The paper microstructures are shown to satisfy standard PUF metrics, making them a suitable candidate for authentication. The paper discusses the properties and security of paper-based physical-unclonable functions, PUFs, for anti-counterfeiting systems. 4 key metrics are identified: robustness, uniqueness, uniformity, and ease of evaluation. The authors argue that paper PUF-based systems satisfy these properties, making them suitable for deployment. The robustness of paper PUF responses is ensured through pre-processing methods that compensate for variations in illumination conditions. Uniqueness is demonstrated through low equal error rates, EARs, in previous studies. Uniformity is achieved globally, even if not locally, due to the weak correlation between nearby pixels in norm maps. Ease of evaluation is demonstrated through the use of equipment such as flatbed scanners or mobile cameras to estimate norm maps. The authors also discuss physical attacks on paper PUF-based systems, including denial of service, DOS, attacks that aim to destroy the texture of the paper surface. While such attacks can reduce the robustness of the system, the uniqueness of the paper PUF response remains stable. The authors propose a general framework for paper-based authentication systems, which consists of 4 stages: image collection and preprocessing, feature extraction, storing reference data, and decision-making. The framework is illustrated using a norm map-based anti-counterfeiting system. The authors also develop a comprehensive taxonomy of existing anti-counterfeiting methods, categorizing them based on physical and cyber world solutions. The taxonomy highlights the limited amount of work that expands ideas to other materials beyond paper. The authors evaluate the deployability of these systems based on desirable properties such as non-proprietary design, unclonability, and the use of standard equipment. The paper concludes by highlighting the potential of paper PUF-based authentication systems for real-world applications, despite limitations and challenges. The authors emphasize the importance of understanding the security of both the physical and cyber worlds in combating counterfeits. This research paper presents a comprehensive analysis of anti-counterfeiting systems, focusing on paper-based authentication methods. The authors categorize existing systems into several categories, including those using specialized signal acquisition setups, commonly available visual acquisition setups, and methods adding extrinsic identifiers to paper. They also discuss methods using intrinsic norm maps as features and blockchain-based storage solutions. The authors highlight the limitations of existing systems, noting that most works concentrate on either designing robust physical world systems or creating secure cyber worlds, but often neglect the other aspect. They also point out that visual features are commonly used, but are sensitive to environmental conditions. In contrast, normap-based systems use accessible and ubiquitous means of image acquisition, physical intrinsic features that are unclonable, and do not add significant cost overhead. The paper then discusses the desired properties of secure systems, including confidentiality, integrity, revocability, replay resistance, and availability. The authors outline the vulnerabilities of the consolidated framework, including attacks on image acquisition, feature extraction, and verification. They highlight the importance of understanding the key threats to each operational stage and provide a set of representative mitigation strategies. The authors specifically discuss attacks on Stage 1, image acquisition, including DOS attacks and sensor spoofing. They note that DOS attacks can render the authentication feature unusable, while sensor spoofing can provide an authentication record for a counterfeit product. The authors propose mitigation strategies, including quality control checkpoints and image forensic strategies. The paper also touches on attacks on Stage 2, feature extraction, which can be influenced by attacks on the previous stage. The authors emphasize the importance of protecting the feature extraction process and propose strategies to mitigate these attacks. Overall, this research paper provides a comprehensive analysis of anti-counterfeiting systems, highlighting the limitations of existing methods and proposing strategies to improve their security. The authors emphasize the importance of understanding the key threats to each operational stage and provide a framework for designing secure paper-based authentication systems. The paper discusses various attacks on a product authentication system, focusing on 4 stages: feature extraction, feature comparison, reference database, and decision-making system. It highlights potential vulnerabilities and proposes mitigation strategies for each stage. In the feature extraction stage, the paper discusses modeling attacks and synthetic feature generation. It suggests using invisible feature forensics modules to detect synthetic features and implementing lockout mechanisms to limit the number of queries an adversary can make. For the feature comparison stage, the paper emphasizes the importance of securing the reference database against template tampering, leakage, and malicious registration. It recommends using blockchains or blockchain database hybrids for securing the database and leveraging concepts from biometrics and security practices such as salting, revocable non-invertible hashing, and biometric crypto systems to protect against leaked templates. In the decision-making system stage, the paper addresses hill climbing attacks by suggesting the use of information leakage-resistant distance metrics or limiting the number of queries through lockout mechanisms. It also proposes using Pearson correlation as a similarity metric instead of LP norms, which have been shown to leak information about raw templates. Finally, the paper discusses attacks on interfaces between modules, particularly replay attacks, and suggests using strong cryptographic protocols like TLS and timestamping to mitigate these attacks. The paper concludes by consolidating its attack mitigation strategies into best practices for supply chains and examining real-world application examples in different scales, focusing on authentication systems based on norm maps due to their numerous advantages. The paper discusses the security best practices for supply chain authentication infrastructure, focusing on template protection, immutable audit trails, physical intrinsic identifiers, signal forensics, distributed infrastructure, and cryptographic security. It also presents 2 application scenarios: a small-scale supply chain with a trusted centralized service provider and a large-scale supply chain with a peer-to-peer model. In the small-scale scenario, the client-server model is appropriate due to mutual trust among stakeholders. The auction house acts as a trusted service provider, sharing information and setting up a trusted infrastructure. The NORMAP-based authentication is non-invasive and well-suited for this application. Security considerations include deploying a small, private blockchain to ensure non-repudiability for audits and protect against potential tampering. In the large-scale scenario, a peer-to-peer model is considered due to the difficulty in establishing a centralized authority that all stakeholders trust. Each node has access to all operational stages of the authentication pipeline and carries out the authentication process locally. Regular communication between nodes and template protection are introduced to secure the process. A mutual authentication algorithm is proposed, where each node acts as a prover to other nodes that their local authentication process was legitimate. However, this algorithm has limitations, such as significant cost overhead and potential information leakage to malicious nodes. Future improvements include running mutual authentication every consensus cycle, checking previously used pairs, and ensuring that creating the hashed norm map via brute force is expensive and infeasible. Here is a combined summary of pages 13 and 14 of the research paper. The authors discuss medium-scale supply chains, specifically in the semiconductor industry, where hybrid models are most suitable due to their balance of scale and security. In this scenario, a semiconductor company, Bob, sells printed circuit boards, PCBs, to Alice's company, which then outsources chip assembly to a factory in a region without trade agreements. The authors propose a design that combines client-server and peer-to-peer, P2P, models to address security concerns. The authors also examine common design considerations across all 3 scales, including the implementation of reference databases, storage, and scalability. They suggest using space partitioning data structures, such as KD trees, quad trees, and ball trees, to improve scalability. Additionally, they discuss the importance of evaluating the cost of infrastructure associated with storage solutions and understanding the trade-off between cost and security. The authors propose a novel idea of creating a holdout reference set to add an extra layer of security to these systems. This set would store a finer representation of templates, which can be used to refine authentication confidence. They also discuss the use of signal processing techniques, such as suband decomposition, to decompose templates into finer and coarser representations. The authors acknowledge that their work is distinct from existing surveys and SoKs, which often focus on the security of hardware PUFs for cryptographic protocols or specific techniques for creating PUFs. In contrast, their work takes a holistic view of anti-counterfeiting systems, evaluating different prior works, exploring multiple systems based on area of application, and performing a systematic security analysis. The authors conclude by emphasizing the urgent need to develop robust solutions to combat counterfeits in the supply chain ecosystem. They highlight that there is no one-size-fits-all solution and that different application scenarios require varying system designs. Future anti-counterfeiting solutions can leverage their analysis as a starting point to formulate practical and secure systems. The references provided on page 14 include a range of sources, from academic papers to patents and online articles, which demonstrate the author's comprehensive review of the field. The paper discusses the use of physical-unclonable functions, PUFs, and mobile cameras for counterfeit detection. It highlights the importance of authentication in various fields, including supply chain management, and the role of blockchain technology in enhancing security. The authors also explore the concept of a blockchain-based database, which can provide a secure and transparent way to store and manage data. In addition, the paper reviews different methods for generating unique identifiers for products, such as using the microstructure of materials or laser surface authentication. These techniques can help in traceability and anti-counterfeiting efforts. Furthermore, the authors discuss the issue of spoofing attacks on biometric systems and the need for robust liveness detection mechanisms. The paper also touches upon the topic of black box adversarial attacks on deep neural networks, which can compromise the security of machine learning models. It emphasizes the importance of developing robust models that can resist such attacks. Moreover, the authors discuss the concept of Chainify DB, which aims to integrate blockchain technology with traditional databases to enhance security and transparency. Finally, the paper reviews various biometric systems and their vulnerabilities, highlighting the need for secure and reliable authentication mechanisms. It also discusses the use of hill-climbing algorithms in attacking biometric systems and the importance of developing robust countermeasures against these attacks. Overall, the paper provides a comprehensive overview of the latest trends and challenges in the field of security, authentication, and anti-counterfeiting. The paper discusses the concept of a decentralized, secure, and general transaction ledger, as introduced by Ethereum 107. It also references Bitcoin's white paper 108, which introduced the concept of a decentralized digital currency. The authors then delve into various data structures and algorithms used for efficient data retrieval, such as multi-dimensional binary search trees 109, KD trees 110, quad trees 111, and octrees 112. They also mention the use of hashing for similarity search in high dimensions 114. The paper further explores blockchain data storage optimizations, including a comprehensive survey 115, and various approaches to distributed file storage and access frameworks using IPFS and blockchain 116,118. It discusses consensus unit-based storage schemes 119, jigsaw-like data reduction approaches 120, and multi-level distributed caching for blockchain storage optimization 121. Additionally, the authors discuss the concept of finite lifetime blocks with applications to edge-based IoT 122, decentralized data processing and immutable storage for multimedia streaming 123, and the use of multirate systems and filter banks 124. They also touch upon scale space theory 125, distinctive image features from scale-invariant keypoints 126, and physical-unclonable functions PUFs, in security protocols 127,130. Finally, they integrate blockchain into supply chains safeguarded by PU-enabled RFID 131.